Hello all, this is a lecture that was not included in the last year when I offered this course. So it's a newly recorded lecture. That's why I have kept the lecture number a bit strange as 5a so that I don't jumble up the sequences later on. Okay, so this is mainly to talk about what are known as soft margin classifiers. This is used when the data is not exactly, not perfectly separable by, let us say, a line or a linearly separable, but almost all of the good points can be separated from almost all of the bad points, right? So in these kind of scenario, we don't want to completely put our towels down and say that nothing can be done. We still want to be able to come up with a approximate classifier. What do you mean by an approximate classifier? We'll quantify it. I mean, the purpose of this lecture is to exactly quantify what this approximate classifier means. But intuitively, what we are going to do is classify as much of the points as possible. And for those that are misclassified, we'll try to find the separator in a way that the misclassified points are not too far away from the separating line. They're on the wrong side of the separating line, yes, but maybe not too far away from it. Okay, so yeah, as we all know, this perceptron algorithm as well as the SVM will fail if the good and bad points are not linearly separable. Now, sometimes we work by going into a higher dimension. I mean, this is, there is a major reason to do that, not just to get an approximate classifier or anything. This use of the kernel trick and imagining the points to be embedded in a larger space is mainly because sometimes the data, the good and bad points, the separation boundary is not linear. It may be a higher degree polynomial, it may be a like a circle, for example, or it may be exponential curve or whatever. In those cases, this kernel trick is, as I told you, mathematically a beautiful trick. But even for the kernel trick, in the space in which you are embedding, you are still asking for a linear separability. In the codomain of phi, okay, we still need linear separability. Otherwise, even the kernel trick will not work. Okay. And hence we ask the question, can we allow for some error in a controlled manner? How controlled and all, we will make precise and ask for approximate classifiers. Okay, so maybe this picture will help you get a feel of what we are talking about. Most of the green points are on the top of the line. Most of the blue points are below the line, but there are a few misclassified points like this. You can see some blue points and some green points are misclassified. Okay, so this is the kind of separator that we are looking for. Okay, so let us before doing that modification, let us quickly recall what was the SVM. Okay, this is the SVM without the kernel, and I am also making this additional assumption that we are only looking for separating hyperplanes which pass through the origin. We know that this can be done without any loss by moving x into one dimension higher. Okay, in fact, this is how we did the perceptron algorithm in class. In the tutorial, we actually worked with the direct model without padding the x. Okay, so but to keep the notation simple and not to talk about b, we will assume that we do this transformation. Your actual data point was this, but we will always consider this as xn1, and then the vector that we are returning, this a1 to an, instead we will think of returning a1 to an and this minus b. This is all these parameters and minus b are things which we have to find out, which either the perceptron learning algorithm or the SVM will try to find out. But we can model this whole thing as a single vector a prime. Okay, I will not call this x prime or a prime. I will directly start calling this x and a. So assume that we are only looking for a hyperplane which passes through the origin. Okay, that's what you have to remember. And the good points and bad points, we also know about this model of specifying good versus bad. Instead of giving two separate sets G and B, we in fact give their union. This X stands for G union B, and this F, what is this F? F of X is equal to +1 for good points and -1 for bad points. Okay, so either you can give it in terms of two sets, or you can give the union of the sets and then give a classifier function as to which is good and which is bad. Okay, so this is the model in which we are working, and aim is to output this A, which is a normal to the separating hyperplane. But what does the SVM do? For the perceptron, all you need is you find an A such that if it was the perceptron, then all you need is to find an A such that inner product of A with X is greater than 0 for all the good points and A with X is less than 0 for all the bad points. Or instead of writing this in 2 lines, using F, I can restate this as, and perceptron will give an A such that inner product of AX multiplied with Fx will be greater than 0. Okay, so when for good points Fx is 1, so this is just saying that inner product Ax is greater than 0. For bad points f of x is minus 1, so this is saying inner product A comma x is less than 0. That's what the perceptron's job is. But SVM has a much more difficult job to do. It is not happy just to find some vector A which does that. It has to find among such vectors the best one. Okay, so what is the best one? The best one is like you look at the minimum such margin where the minimization is over all x in the good and bad sets, right? Among all points, you find the point where this margin is the smallest, but now even for that smallest margin, you find out which A vector or which hyperplane will maximize the smallest, maximize that nearest point. Okay, so in some sense we are trying to maximize the distance of the convex hull to the separating plane. That's what we are trying to do. And since there is a slight vagueness here, because this is an inner product, this grows linearly with A. So maybe after all this, while SVM finds out returns an A, and then somebody can say that, oh, I have a better algorithm than SVM. All I do is I do an SVM with a post processing, where the post processing is just multiplying A with 10. Okay, then this maximum value here becomes 10 times what the SVM gave you. Okay, so in order to avoid such cheating, or to make the comparison on a fair ground, in the sense that we are only comparing the angle of the plane or the direction of the normal, and we are not going to really play with the magnitude of the normal, which in fact does not really make sense, because we are only looking for defining the plane. Okay, any vector that is normal to the plane will define the same plane. So playing with the magnitude of A is cheating. So in order not to do that, we restrict our attention only to unit vectors A. This is what the SVMs attempt to do, but as I hinted in the last class, usually this is not how the optimization program is given to a optimization routine, optimization solver. Instead, we kind of invert the role of the cost function and the constraint. Okay, and it is not difficult to see that this will kind of give the same answer. Okay, we are trying to minimize the norm of A, or equivalently the norm of A squared. It is the square is introduced so that this function is differentiable. Okay, so we try to minimize the norm of A, or norm of A squared, subject to the condition that this minimum AX fx, or equivalently saying for every x, this AX fx has to be at least 1. So you fix the margin and find the smallest norm which violates that. Okay, so among two vectors, if this guy, if this A vector as well as this A vector are both separators, and when both ensure a margin of +1, then this is surely better, because the separation is not coming by virtue of A's own magnitude, it is coming by virtue of A being in the correct direction. That is the intuition behind why this is working. Okay. Yeah, so this much is what we have already seen. I'm just restating it without that second parameter B, or the n+1th parameter B. Now, what is the attempt in this lecture? Our attempt is to move from this hard margin, or a hard margin like this, to a soft margin, or equivalently, instead of having a very rigid constraint like this, you are saying that unless this happens, for example, this to happen, the points have to be linearly separable, right? Because for points where fx is positive, fx is +1, this AX inner product has to be positive. and for the bad points, that is when fx is negative, in order to satisfy this, inner product ax has to be negative. So there is no room for, no compromise permitted, no tolerance permitted, and hence this is, once you put a constraint like this, there is no question of an approximate classifier. So instead of this constraint, we try to convert this constraint into a penalty and try to add this penalty to the cost function. Okay, so penalty is something which you pay, but still, I mean, you can still, it is not a veto. You don't just rule out because of that. Okay, so instead of saying your inner product ax times f of x is always greater than or equal to 1, we try to penalize this quantity, this 1 minus this inner product a of fx, but this subscript of plus. Okay, this is a thing that I want you to notice. This notation is something which we will use. When you say z plus, what we mean is that if z is already positive, you take that, but if z is negative, then you take it to be 0. Okay, so that is what this z plus function will look like. So if you plot this z plus function on a curve, as long as z is negative, maximum of 0 and the negative number is 0. So as long as z is negative, you get like this, and once z is 0 or positive, then the max becomes just z. Okay, so this is the curve. If this is z, this is z plus. Okay, so here we are applying this plus to this quantity 1 minus inner product of ax f of x. So what does it do? So as long as this quantity is negative, which means f of a, this side is greater than or equal to 1, which means this constraint is met. As long as this constraint is satisfied, the penalty is 0. But once you violate the constraint, you pay a penalty equal to the amount by which you violate the constraint. And the amount by which you are less than 1 is what this is. Okay, so that is the idea. If you are seeing this for the first time, please pause and try to internalize what this penalty means. Okay, now technically speaking, you can use any non-decreasing, okay, not even increasing, any non-decreasing function of this quantity as your penalty, but most of the time we will just use this directly. Okay, by the way, remember this is for 1x, but we have to check this constraint. Remember, this constraint is for all x, right? So we have to check this for all x, which means we are going to really add up all these penalties. Okay, so this, once you add it up, once you add this up, this is called a hinge loss, and this is a very popular term when it comes to all these soft margin classifiers. Okay, so what is the hinge loss? So this will depend on all these three things, right? The input, which is x and f, it will depend on x and f, and it will also depend on the current solution a. Okay, and how is it computed? It is this 1 minus inner product ax fx with this plus operator, but now you sum it up over every x in your domain. Okay, the good and bad points are automatically taken care because of this fx, but if you want to write them separately, you can also write it like this, as over the good points, since fx is plus 1, this is just 1 minus inner product of ax. Over the bad points, since fx is minus 1, this becomes 1 plus inner product ax, but don't forget the subscript plus. Okay, so that has to be retained in both the places. So this is the hinge loss. Now, how do we add this penalty to the cost function? Yeah, we just add this penalty to the cost function, but we use a multiplier lambda, which is a tunable parameter. This is a penalty factor. Okay, in the sense that by you increasing the value of lambda, you are kind of penalizing errors much more. Decreasing smaller values of lambda means, okay, your penalty for this loss is very low. Okay, so yeah, I think this is wrong. Lambda equal to 0 will not imply a hard margin. Actually, what will imply a hard margin is lambda, which is much larger than a. Okay, so maybe it will be clear 2 lines down the line. But again, remember that this lambda is a penalty factor. Okay, so yeah, so and what are there any constraints left? No, now you do not have any constraints in the system. All the constraints have been softened out, can been softened up by converting it into a loss function, and that is added to the cost function. So we have now just to solve an unconditional optimization problem. Okay. Now this optimization problem is there are many techniques to solve it. I'll remark about this cost function in a moment. But before going there, this idea of moving the constraints as penalties into the cost function has become so popular that now people almost think about this cost function in the opposite way. Okay, they kind of have already started tying the horse behind the cart. They write it as a loss plus a factor times the norm squared. Okay, so usually they write it as LA of AXF plus some eta times norm of A squared. You say that there is nothing different here, but yeah, there is nothing different between the above formulation and this formulation, but this is what you are more likely to see in literature. And this first term is correctly referred to as a loss, and the second term somehow is just referred to as a regularizer, which somehow another reason I think why this is popular is without all this build-up of this theory and all this the mathematics behind this optimization, one can easily think of this as some kind of a loss, and loss is something what you always want to minimize, and this kind of ensures that you are not minimizing the loss by actually shrinking the norm of the vector. You kind of retain the norm of the vector there to be fair to small vectors. Okay, so I don't like that intuition, but that's probably one reason why this is a more popular model. Okay, now a few small remarks. Why is this called the hinge loss? That is because if you look at this 1 minus z plus, okay, then this has this formation. Okay, this is nothing but you can once you had seen this graph, this is just a mirroring and a flipping of that, because instead of z you have 1 minus z. So this is the plot of this 1 minus z plus. So this looks like a a door hinge that we see on our doors, right? So that is why this is called the hinge loss. And second, why is this cost function, either in this form or in the form where the lambda sits with here. Okay, why is this so popular nowadays? Because of three properties. Okay, so firstly, this is a convex function. Okay, so I hope you understand what is a convex function. In one dimension it is easy to draw. Okay, if it's just a single valued function, you have an x and an f of x. A convex function is something which looks like this, like the function of an x squared and so on. The formal definition of a convex function will be, if you take 2 points, say x1 and x2, right? Now you calculate f of x1, which is this point, f of x1. Then you calculate f of x2, that is this value. Now you take any point in the middle. Okay, so this is not necessarily exactly in the center, somewhere in between x1 and x2. So this is some x1 lambda plus x2 into 1 minus lambda. Okay, then you also calculate what would be f of x1 times lambda plus f of x2 times 1 minus lambda. That has to be above the true value of f of x. Okay, then it is called a convex function. I think there is so much of a clutter here. Let me properly write it down. So definition, a function, let me write it in a more generality when I write it, from Rn to R, okay, is called convex. When do you call it convex? Convex if for all x1, x2 in Rn, we need that above condition to be satisfied, which is we try to evaluate f at lambda x1. By the way, this lambda x1 plus 1 minus lambda x2 makes sense even when x1 and x2 are vectors. Okay, remember x1, x2 are n-dimensional vectors. So this is a point in a line joining this x1 and x2 in the n-dimensional space. Okay, based on if lambda is very small, this will be close to x2. If lambda is very large, it will be close to x1. Okay, for all x1, and I should say for all lambda in 0, 1. Okay, so that the point is in between. What do I want this value of the function to be? Remember, the function's value, which is here, is small. Function's value, which is here, is, and that is lower. Okay, so this is lower than or equal to which quantity? Lambda times f of x1 plus 1 minus lambda times f of x2. Okay, such functions are what are called convex. Okay, now we already saw what is a convex set in the first lecture itself, right? So these two have the same names, but at least the convex set is much more easy to visualize. You just have to say that the line segment joining any 2 points is inside of this. Here we are saying that the line segment joining any 2 points in this graph kind of goes above, or the function is below that. Okay, so maybe, I'm guessing here, maybe one reason why both this word convex is used in both the scenarios is, if you think about a convex function like this and think about the region above that curve. Okay, so what is the region corresponding to this I'm talking about? This is all the points in your in which space. This is an R2R function. If it's an R2R function, you already are talking about points in R squared. In general, you will be talking about points in R n plus 1, where, okay, here let me write it, xy element of R squared such that y is greater than or equal to f of x. Okay, that is this region, this shaded region here, right? In 3 dimension, instead of this curve like this, in 2 dimensions, this if it was a function from R squared to R, then this curve, instead of this curve, you should visualize something like a bowl. Okay, if you visualize a bowl, and then this is the whole volume above that bowl. Okay, so that is what this is. So if it's a general function if f is from some Rn to R, what would this be? It would be all those points, x1 to xn comma y element of Rn plus 1 such that y is greater than or equal to f of x1 up to xn. Okay, I shouldn't have gone to these details, just to give an intuition. So the intuition is that this set is convex. Okay, so if you join any 2 points, the line segment joining any 2 points in this set is entirely inside that set. Okay, so f is a convex function somehow corresponds to this Rf being a convex set. Okay, so maybe that is why both the word convex is used in both cases, but as I told you, I'm guessing here, maybe there is another deeper reason which I do not know. Okay. But why are convex functions so popular in for optimization problems? That's because convex functions, we are going to find the minima of a function. So convex functions have only one minima. Why? Let me not prove it rigorously. Suppose you had two. By the way, when I say there is what I'm trying to say is that when I said a minima, I meant points where this f prime of x is equal to 0. Not talking about the global minima. These are called local minimas. So I'm saying a convex function cannot have 2 local minimas, because if you visualize a picture like this, then you draw a straight line like this, you see that the value of the function is above this straight line, which violates the definition of a convex function. So for a convex function, if you find a local minima, that's also going to be a global minima. There are small exceptions where if you have a flat base like this, okay, if you have a flat region like this, then all of them are global minimas and this is still convex. Okay, but this I am kind of ignoring. This kind of structure will not be there if the function is differentiable, which is the next condition. Okay, so this is one reason why convex functions are very popular. But that's not the entire story. They are also popular, together with differentiability. If the function is differentiable, then you can use this very powerful algorithm called gradient descent to solve them. Okay, maybe I would not go into the details of gradient descent. I might rather, you can either most of you would have already seen a gradient descent algorithm. Otherwise, again, a quick search will reveal good lectures on gradient descent. Okay, because gradient descent uses the gradient, which is nothing but the higher dimensional equivalent of a derivative. So a function being differentiable will give you a gradient descent. So you can see that the norm of a squared, the reason why we put a square is that so that it is differentiable. By the way, differentiable with respect to what? Differentiable with respect to the a vector itself. So we will be taking dou by dou of a1, dou by dou of a2 and so on up to dou by dou of an. This is together with this is what will be the gradient vector. Okay, so you have to, so this norm of a would have been difficult to differentiate. It can still be, but it's difficult to differentiate, whereas norm square is much more easier to differentiate, and on differentiating you get a linear term. What about the hinge loss? Hinge loss is almost differentiable except at this one point where it is continuous but not differentiable. So that is a minor problem. So there are other loss functions which is much more smoother, so that differentiation, it is differentiable. But this is still more popular because even though you can really not differentiate it, you can arbitrarily set the gradient here to either the gradient of this side or the gradient of this side. Okay, these two are different. Here the slope is 0, here the slope is -1, but at this point you can either set it to 0 or -1, or in fact anything in between. Gradient descent will still work. In fact, this method technically is called the subgradient descent, where you don't work with a gradient but with a subgradient, where but let's not again get into the details of that. So these two properties are very important, but there is also a third property, which is that this entire function can be written as a sum like this. Now this term does not involve the data points. This term is what involves the data points, but this is a sum over all data points, and each component in the sum only involves one among the large number of data points that you can have. So this is extremely useful in a variant of, not a variant, in an algorithm called stochastic gradient descent, where instead of calculating the entire gradient in each step, you randomly pick one term of this summation and calculate the gradient only based on that one term. It looks very counterintuitive as to why it will work, but this is the idea behind stochastic gradient descent, and you can, because of this finite sum nature of this function, this would have been, because of this finite sum nature of this gradient, you can use a stochastic gradient descent even. Okay, so that is how this is, SVM is usually solved in practice. Okay, so what I want, this is a short lecture, but I want you to spend this extra time on trying to, at least the interested among you, I highly recommend that you look at videos which talk about gradient descent as well as stochastic gradient descent. Both have very, at least a gradient descent, intuitively you should know as, you should imagine yourself to be this, you should imagine a three-dimensional scenario where your function, you should imagine a scenario where f is a function from r squared to r. Okay, so I won't be able to draw it because it's a three-dimensional picture. Your domain itself will have some two coordinates, right, x1 and x2, and the f value that you evaluate at any point, you kind of imagine it as a region like this. Okay, a region like this, right, and this may be more like a sand dune kind of a same. Okay, at least in my mind, how the picture that comes to my mind is that of the sand dunes in a desert. Okay, so x and y are your normal x and y, or x1 and x2, the two horizontal axes, and the height of the sand dune is what the value of the function is. And your aim is to find a local minima of this function. Gradient descent in its vanilla form will not be able to find a global minimum. It is looking for a local minimum. So suppose you are standing on at this point, right? You don't have the full view, right? You cannot compute the function at every location. You don't have a full view. You can even assume that you are blind. Okay. Suppose you are inside the dark. It's late in the night. You cannot see anything, but you want to reach a minimum. What would you do? You'll try putting a foot on each direction around the thing, right? So that you kind of trying to gauge with your foot in which direction the sand dunes is sloping down. and whichever direction seems to be sloping down the maximum, that is the direction that you want to take. Okay, so now the gradient, mathematically this translates to trying to estimate the gradient of that function or the slope of that curve at that point. The gradient would actually point to the direction in which the slope is increasing the maximum. So you actually step on the opposite direction. So you calculate the gradient and then go back, right? So each step, if you have a current A vector that you have calculated, you will update it by this gradient of this total function. Okay, and you usually put a step size here to control this, and this you repeat as many steps as till there is very little change in A. This is how a gradient descent usually works. And in the stochastic descent gradient descent case, if your f is of the form some sigma x element of x fx, then every step you, instead of doing this whole gradient computation, you only compute the gradient of fx, where x is chosen randomly, x element of x randomly. Okay, so this is the, so these algorithms are available for SVM to complete its trick. Okay, so now to summarize, either you can, this is one approximate route that is very popular when data is not really separable but almost separable, then you use a soft margin classifier like this. Okay, thank you.